All right, recording has started.
I guess I can, well, first off, welcome to this very special session of the seminar. Thanks again, B, for getting us started. SJ, are you there?
Yes, hello.
Hey. I think in this case, I will let SJ take the introduction, and then let's looking forward to an exciting discussion.
Yes, thanks so much, David, for joining us. Uh, Everyone, I'm delighted to have David Bown joining us. We initially thought that he might give a talk in an earlier seminar series when NDIF was still a more of a glimmer in the eye before it had gotten off the ground. And it's always been a project to build public AI, to build AI for public use, and currently supported by the NSF in the US for, but it's an approach to making infrastructure available across institutions and finding ways to specialize where pieces of infrastructure are provided and how it's administered and gets directly into the mechanics of what it looks like to maintain infrastructure for the use of the entire community. So uh, I can't wait to hear how things have been developing in the year that it's been online. And uh, we also have Sigurd Schacht joining in the chat,
Yes.
which is fantastic. When I saw David a
And
couple of weeks ago,
Karsten
he
as well.
mentioned, oh, and Karsten, wonderful. And so the idea has already been taking root in places outside the US. So maybe we'll also get to hear what uh, what of the lessons from the initial project are.
It's That's great.
Yeah, are most the most tractable in other contexts. Take it away.
Thank you, Sam. Um, yeah, it's amazing to see Sigurd and Karsten here as well. Um, so I guess I'm gonna talk about the National Deep Inference Fabric project here, but I'm gonna spend maybe half the talk motivating it. But I'm not that familiar with the group here in the audience and what issues animate you. So I'm very comfortable to make it interactive if you have questions or if you'd really rather me drill into a certain thing that I've mentioned, then feel free to interrupt. And I have a lot of different things I can talk about. Okay. So this talk is I'm repurposing a talk that I gave uh, to the administration, to a bunch of federal agency folks in the U.S. about what the heck it is that we're doing with NDIF, and so I sort of gave this talk, a couple months into the Trump administration, and I've rejiggered the slides a little bit here, but one of the um, questions that is animating the United States right now is how to build leadership in AI. And so I began with this framing, but I think that one of the points that I want to make is that the leadership is really a human thing. It's not about the chips. And so the story that the story of large scale AI that's being commercialized today is this funny long story that begins in the 1940s, really, but maybe for systems that people built in the 1960s, where repeatedly people have tried this idea of creating systems that work via machine learning, and the scientists who sort of support the idea at one level, they are very optimistic about what this machine learning technology can create, but at another level, uh, you know, they keep on giving up on the idea when it turns out that it doesn't really work out as well as they might have thought. So this sort of this cycle of AI started in 1962 with Rosenblatt's perceptron. He wired together 64 learnable parameters. I guess if you have a neural network with 64 learnable parameters, but you have to wire together every single one, that's physically what it looks like. I'm always fascinated to look at Rosenblatt's physical computer that he's created there in the upper left corner. You can see 64 parameters, 64 parameters in there. I think each one is probably a physical potentiometer that maybe has a motor attached to it or something. And so but he was able to get the system to learn something. That's actually quite a feat, quite amazing back in the day. Uh, eh, that approach to AI was went out of fashion for more than 20 years until the 80s, when maybe it was still out of fashion in the 80s, but hardy band of LeCun and Hinton sort of brought it back. In Southern California and in other places to um, to create the 1980s version of deep nets, which again sort of went out of fashion for another 20 years, and we've continued to have these cycles where each time the idea of machine learning has come back, and people have realized, oh, this idea works better than we thought it did. And the funny thing about each one of these cycles is that really every time we go around this cycle, we've really been just doing the same thing. It's been the same kind of machine learning, uh, and really the thing that we've been doing is we've been training them on more data. We've been making the systems bigger, and and we've been surprised. We've often surprised ourselves at how well this works. Um, I know that when GPT-3 came out, and it was able to do meta learning, it was a real shocker because all the thing is a language model. All it does is predict the next word. It's something that we've been doing since the 1980s, right? It's exactly the same architecture, at least the loss function. It's the same loss function that we apply. There's a couple little tricks in the neural networks, but the main thing that we've been doing is making these systems bigger. And I have to say that let me see. Yeah, so let's see. I have a comment here from Bateau. Oh, actually, I'm going to put this comment in different order here. Um, so one of the lessons that you can draw from this. Who here is familiar with the bitter lesson? Raise your hand if you know what the bitter lesson is. Okay, yeah, maybe. Is it really half of you, or only half of you are raising your hands? Maybe all of you know what the bitter lesson is, right? Um, so, but so this the way I drew the slides here is another way of showing the bitter lesson, which is you know every time machine learning goes out of fashion, people think, oh, surely there's some way for us to improve these systems by incorporating some human genius into it, and we do that for a decade. But then what the bitter lesson is that actually the more productive um, approach over the last I guess 70 years has been to instead turn back to machine learning and just figuring out how to get it to scale, either machine learning or search algorithms. And so researchers who seek to leverage their own human knowledge end up hitting dead ends, whereas in the blue here, the thing that matters in the long run is leveraging the computation. So basically teaching these systems to learn from themselves has been the pattern. And that's the cycle that we're in right now. Now, I think that there's still an ongoing debate. people would debate that here today still. Um, but the big cycle that we're living through right now is, the entire AI industry believes in the bitter lesson, and they're plowing trillions of dollars into it based on this assumption. That's the current culture. But here's the bitter part of the bitter lesson. What's really bitter? Okay, so this is a sweet part of the bitter lesson is, well, it actually seems to work. Maybe it's quite expensive. You do have to spend, hundreds of billions of dollars of electricity to climb these curves, but climb the curves we do. The systems they do seem to genuinely be getting stronger and better the more people invest, into training them on more data with more computation. So one of the uh, one of the fun benchmark uh, measurements is GPQA Diamond, which is uh, kind of PhD. They say PhD level science questions. Um, and the systems really are getting better at them. Uh, so so uh, that's like rich set network. So the bitter part of the bitter lesson is if you superimpose on this, how are we doing? Is this creating a big boom in the computer industry? Are we hiring a lot of software engineers to power these advancements? And the answer is no, not really. Actually, we're in this huge decline. This is the Federal Reserve statistics on how many, software development job postings, there are every month, and it's I keep on looking for the boom here. When there were previous booms, when there was the internet boom or when there was the mobile boom in technology, um, these all created a massive demand for app developers, webmasters, people needed to plow into these industries to create everything. Um, and I'm not seeing it so far in AI. And I'd say, ooh, is this also Rich Sutton at work? Is this the bitter lesson? Is the hard part of what's going on here all done, with computation? So this is kind of the question, and this is something that I fear for public AI reasons. Um, and so one of the questions, that sort of motivates this talk is this really the world that we're building? Is this what we want to be building? Or is there something missing here? And so there is something missing here. I'll put this slide up from this is Bateau. He got back from ICLR 2025, and he said, there's actually two things that are going on in AI, and all of the all of the attention is going on with one thing, but from his point of view as a scientist, the interesting thing is happening in the second area. So all the attention is being paid to what AI cannot yet do. AI cannot yet, uh, get 100% on that GPQA exam. It still has mistakes. It can't do all the scientific reasoning. It can't fully replace a human, who has a PhD. Maybe some humans, but maybe not all humans, or something like that. And it can't do long-term reasoning. These AIs we're still struggling with hallucinations. When you back them into a corner and tell them they got to give an answer, they're quite happy to make something up, and they still are. And we're having a lot of trouble, dealing with a number of issues like this. And so you go to ICLR and you see, a lot of people talking about these things that AIs can't do. On the other hand, these AI systems already can achieve a whole bunch of tasks near perfectly. And there's this other thing going on, which is even though they can do it, they are a surprise. We have no idea how they do the things that they already can do very well. We don't know why they can conduct a fluent conversation and hold the topic, why they can follow instructions, how they can do a bunch of other things that they seem to be able to do effortlessly. Uh, these continue to be mysteries to us. And so Bateau's point of view is, even if you're interested in trying to make AI stronger, how do you expect to be able to do that if you don't even understand how AI is doing what it is doing today? And so his encouragement to scientists is to try to understand this problem. And so I guess I should make a slide for this, but what my name for this phenomenon that Bateau is noticing is is the bitter inversion. So the bitter lesson really is about advice about what we should and shouldn't do if we're trying to make AI as smart as a human or smarter than humans. If we're trying to make AI smarter, then it might not be the best advice for us to try to teach an AI to think like a human, because maybe we should let AI think the way it's going to think, right? Let it learn itself, right? But when we start getting into the domain where AIs are doing things that we don't understand, where AIs are, uh, starting to cross the boundary, um, and uh, where there's a larger and larger gap between what AIs can do and what humans understand, then it's actually really important for us to understand them. And um, and so I'd call this the bitter inversion, right? It's the other end of the bitter lesson. After you apply the bitter lesson for 70 years, you end up with these systems that we don't get, and now we have to understand them. If we're going to take responsibility for these systems that we deployed, then some person has to understand, at least do a good effort at understanding what the heck it is that they've learned. And in this case, the human understanding is not like an optional part. It's actually the point, because the point is not to make the AI smarter. The point is to make humans smarter about what's going on with AI. And so okay, so what I'm going to talk about here is, oh, this is great. Let me cancel this call. What I'm going to talk about here is how interpretability is the name that we have for this kind of work, and how infrastructure is necessary to plow this forward. So there's really three fundamental things that we're trying to do to um, in this work on interpretability, which is, we're trying to build an ecosystem to allow AI to be deployed in society in a more robust way, where people can actually take responsibility for what the AI is doing. And we think that there's three parts of taking responsibility, three parts of what I call resilient deployment of AI, which is, you know, somebody needs to understand the AI. Somebody needs to know what the AI knows. And then the second stage is that it can't just be abstract understanding. It has to be actionable, right? It has to, we have to be able to have technical measures for taking control of the parts of the AI that we care about, right? So we need methods to control AI. And then there's a third part, which is we actually need to be able to do it in practice, right? It's not good enough to have the mathematical capability to do this, but we actually need the power to do it and the culture around that. And uh, so the interpretability question is, so now the reason that so we do a little bit of this in the field, these three things, but not enough. And the reason is because there's this underlying question underneath the whole thing, which is, after we train a large scale AI, is it even possible for humans to understand it? And I'll say, if you go to deep learning practitioners and you ask them this, I'd say that even today, the majority opinion is no. People who are spending hundreds of millions of dollars of electricity on creating these things, if you ask them, is it possible to understand what it is that the neural network is doing that you just trained? Most of these engineers will say no. Now, a few of them will say yes. Um, Part of our mission in the interpretability academic literature is to try to revive human belief in the power of the scientific method, that it is possible for humans to understand difficult things. But one of the things that's really difficult is that a large fraction of the practitioners in the field have basically given up on this. They think, so they confuse the bitter lesson with this like bitter impossibility. They confuse this idea that it might not be the most productive use of their time to try to teach an AI how to do things the way humans do, right? It might not be the most profitable route with this other thing, which is, oh, it's completely impossible to find an intersection between what humans can understand and what AIs have learned. And which you know, but that's where the field is right now. And so what I'm going to show you is and then even that they say is even understanding even necessary. I think that that's where we are today. And so here's why, a little bit of why it's necessary. So there's just very obvious situations. And so, but I think that a better example than this, I'll just show you this example here. So if you go to DeepSeek R1, most popular reasoning model that's open parameter today, and you ask it about anything going on in Chinese history, then you'll get this model saying that I don't really know anything about these controversial things in history. Tiananmen Square, what year are you talking about? 1989? I don't, that year doesn't exist to me. I know about math and computer science and logic. Let's go play some games. And so now, is it true that it doesn't actually know anything about Tiananmen Square, the Tiananmen Square massacre, right? Is it true? It's not true, right? So if you go into the model and you force it to run in a slightly different way than it was directly trained, then you can get different outputs from it. So this is a very simple, I'll call it an interpretability technique, but it's a very simple technique called pre-filling or thought token forcing, where it works like this. So the way these reasoning models work is that they generate thought tokens, an internal monologue that they normally keep to themselves before they produce their output. But they produce this internal monologue the same way that they produce, text that they say to you, and they embed all the internal monologue inside think tags, like they're written here, like HTML tags, and so the idea here is that even though my question is in green, what happened at the Tiananmen Square protests, I will pre-fill a little bit of the thoughts for this model by saying, okay, now we're going to begin to think, and your first three thoughts are these three words. I know this. And then after I tell it its first three thoughts are I know this, then I'll just let it think whatever it wants to think. And then with that tiny little perturbation, it's like a confessional. It's like everything it knows about Tiananmen Square starts pouring out. It was a complete lie that it has no idea how to approach this type of question. It totally knows how to approach this question. What it knows is it shouldn't say anything. But if you tell it that, it knows something about this, then it'll reveal all its knowledge. So there's this gap. There's this obvious gap. So the reason this is a really nice example is because in R1, there's this very obvious gap between what the model knows and what the model claims to know, right? So it raises, so you have this question, is it even important to understand what a model knows inside? Why can't you just ask it? It'll tell you what it knows. And the fact is, no, it's not guaranteed to tell you what it knows. There may be reasons that it has not to tell you that. And this is an example of that situation. We have plenty of examples like this today. I think that Grok on Twitter is going around misbehaving every day. It's clearly trained with some hidden agendas as well. It's got a similar situation, maybe with different politics. But this kind of power structure is all over the place, and it directly speaks to the fact that that it'd be useful to know this. So John Rotter, one of my PhD students, developed a crawling method based on this to try to crawl all the forbidden topics from inside models. And so instead of just finding out what you know about one forbidden topic, he can elicit thousands of forbidden topics by recursively crawling and getting more of these. And so if you do it in different languages, you get different things, um, which is interesting. And you can do it on other models trained by other people to get a sense for what topics are forbidden in different things. And so you can see the difference between American culture and Chinese culture here. Certainly, there are things that American trained models are very, very reluctant to talk about as well, especially sexual content. They're very reluctant to broach some of these subjects. Um, but in China, there's a big wall around a wide variety of political topics, and it's useful to know this. Um, the so now so it's also useful to know even when it's supposed to be removed. So Perplexity is an American company that is offering a fine-tuned version of R1 to their customers. And because they're a US company, they wanted to remove all this Chinese censorship from the model. So they devised a way and they published a little paper on how to remove the censorship from the model. They did this. And so I told John, oh, this is great. Go and run your crawl on the model. And he did. And what he found was that the model, even though they claimed to remove the censorship, it seemed to not be very different from the censored model originally. Like the Perplexity decensored model was still almost as bad as the original. And he's like, I must be like something must be wrong. Like it's not just his crawl. Like he could after his crawl found some prompts, he could just have relatively ordinary conversations and the censorship would be very, very obvious. What is Perplexity doing? Aren't people just going to notice that their system doesn't work? So I told him he can't just publish this, without at least having a conversation with the Perplexity engineers to tell him, here, ask him if we've tested something wrong or something. And so the Perplexity guys, they were surprised by this measurement. And it turns out after a few days of debugging that the issue was that the Perplexity team had decensored their 16-bit model, their 16-bit version of R1. And then after that, to deploy it, they quantized it down to 8-bit and then deployed that thing. And of course, John measured the deployed one, the 8-bit one. And it turns out that when you quantize the model, all of the censorship comes roaring back. And the Perplexity people hadn't noticed that just rounding down all the numbers, right, quantizing them, has this dramatic effect on the decensoring operation that they did. And so we have to measure, right? Even people who have the best intentions, we need to have ways of double checking them. And so it's just I think it's a good story. So the first ingredient for interpretability in AI is understanding AI. And I'm gonna just flip through some of the state of the science of what people are doing to understand things. So AIs contain a lot of knowledge. So if you narrow it down scientifically to like very specific knowledge that they know, you can narrow down to their word prediction capabilities. So if you have a sentence like Miles Davis plays the blank, and you ask a language model to complete that sentence, and if it's been trained on enough real world text, it knows that the right answer for that is trumpet because it should know that Miles Davis is a famous jazz trumpeter, and he wouldn't say Miles Davis plays the piano or the drums or something. And so this word completion task reveals a little bit of knowledge in this thing. And the question we have is, can we understand what knowledge is in the model? Can we understand where to look for the knowledge, how it's organized? Can we edit it? And to get a handle on this, what the scientists have been developing is a bunch of techniques. One of the techniques that is really effective is causal mediation analysis, which works like this. you run the model twice, one where it reveals its knowledge, and another time where it's doing something else. So for example, here we're just adding some noise where you would say Miles Davis, and then because the noise is there, it can't predict trumpet. It doesn't know the answer anymore. And then we ask, well, in the clean run above, did the model do something that caused it to recall trumpet? Maybe what we can do is if we transplant each one of these hidden states down below, maybe some of them will have the effect of eliciting this behavior that the model knows something about trumpet playing. And most of the time, when you pull down random pieces of the computation, it doesn't have that effect, doesn't work. But rarely, once in a while, you bring something down, and it does cause the model to say, "Haha, somebody is a trumpet player here." And so you can use this type of causal analysis to see which neurons cause an effect, to narrow down what the path is through a transformer. So the transformer hidden states form a big grid, over the text. And if you take sentences that have some knowledge, like Megan Rapinoe plays the sport of soccer, and you take those states and you patch them over to some other sentence, like Shaquille O'Neal plays the sport of basketball. If you patch states in the right place, then you can find that there are certain states that cause the model to think that Shaquille O'Neal plays soccer, and those states are not everywhere. So the transformer is not completely diffuse or chaotic in its computations. It's actually pretty concentrated. There are really two spots, pretty clearly where the model is thinking about what sport, Shaquille O'Neal plays, and at either one of these locations, you can get it to flip. And what one of the things that we've been doing is trying to understand what the function is of these specific locations inside a model. Um, the last location over here has to do with the syntactic activity of saying the word basketball or whatever word you're going to utter. But these earlier locations have to do with the semantic idea that somebody plays a sport, soccer. There are very interesting results we have here about these earlier layer concepts being language independent and other things like that. So scientists are starting to understand how these internal pieces of knowledge and concepts are being represented, and you know, and what we're really converging on as a field is, I'd say, um, a uh, um, uh, you know sort of a three-part research program for how to map out what a large-scale AI knows. One is there's this basic question of what concepts does an AI represent inside? Or if you want to use a less loaded term, like what information does it carry? And so different parts of the AI are basically these vectors of neurons, these big bundles of neurons, and you can ask when you have a big bundle of 1,000 neurons, what information do they carry? So that's one of the key questions. And so for example, neurons at this location here might carry properties of Miles Davis, what instrument he plays, what kind of music, what kind of profession he has, where he's from, what century he lived in, that type of stuff. Um, and then, but then, uh, but that's like the momentary thought that you might have. There's also the question of what knowledge is stored in the model, which the consensus is that the knowledge is more stored in parameters of the model as maps from questions to answers. And then the third question is like what reasoning is embodied in the pathways through the model. Like how does the model compose knowledge and come up with new things that it might not have seen in the training data and generalize. And so that's really about understanding these pathways that vectors take as they go through the model. Now, this is a rough, map of a research program that there's like three things to understand. But all this is like sort of ongoing science of what's going on here. So okay, so there's this ongoing science of like understanding what's going on inside AI. Uh, that's fine. why do you want to do that? Well, the hope is that once you understand it, it gives you tools for controlling it. So one of the examples of that is like once you can locate where knowledge is in a model, then it allows you to be more surgical about changing that knowledge and fixing it. And so, so I won't go into the details of this experiment here, but basically, if you use standard fine tuning to edit a model, you will often change things that you didn't intend to change, have all sorts of unintended side effects, or on the flip side, you will sometimes tend to overfit and not generalize your change to the things that you're hoping to generalize. But if you understand what levels of abstraction are stored at what layers of the model and you focus your fine tuning on those layers, then you can have a more precise effect in the model. And so it's a little bit about like if you can understand, what models are thinking and how they think about it, then you can teach them a little bit more effectively. So I'll just show you a simple um, example of this. In diffusion models, it's well understood that they suffer from bias amplification. When you ask a diffusion model to draw a picture of some doctors, you'll get a picture like this, where all the doctors look a certain way. I don't see a doctor that looks like my doctor, happens to be female. I don't see anybody that looks like her in this picture. Um, but what you can do is, you know, inside these models, it turns out that they do have a piece of knowledge that maps between text that means doctors to another vector, which is like what doctors look like. So this association between how you say doctors, how you ask for pictures of doctors, and what you should draw is just it's just some layers in the diffusion model. It's just some layers in the neural network. It's just in these cross attention layers. And so you can go into these layers and you can intercept that. So let's say we wanted to say, no, doctors doctors are like 50-50 female or whatever fraction we want, right? What we could do is we could find some new vector that represents like 50-50 male female doctors and substitute that for V. Now the problem is maybe we don't know what that vector is, but what these students figured out is that you can get a vector out that says this is what male doctors look like by just asking the model, I want male doctors, and then it'll give you a very clean vector that is just all male doctors. And you can ask for a vector that means this is what female doctors look like, and the models are able to do that. And then they just guessed. They said, well, what if we wanted an equal mix vector? Well, they're vectors. Maybe if we just search on the line between these two vectors, we'll find an equal mix vector somewhere on that line, just linear interpolation. So they did a grid search, and indeed they do find this nice vector that they can patch into the model. And when they do that, then they get, outputs that look like this. So actually, this is a little bit of a show off because they've also done some racial diversity as well. So they've searched over a little bit larger subspace. And so to find a nice diverse mix that they can put in there. And the neat thing about this is it just takes a few minutes and it's very precise. And it's much easier than trying to curate millions and millions of images and hoping that you get rid of the biases in the model. And so they showed that you could use this technique for a bunch of things that have societal impact. A lot of artists are concerned about their very distinctive artistic style being aped for pennies on the dollar by these diffusion models. And so you can go to a model and you can tell it that fancy style that you memorized, erase that. I don't want you to know that. And in a minute you can laser that out of the model. I showed you the bias example, or another example is nudity, right? So these models, they tend to produce nudity in a lot of situations where you don't even ask for it because of the nature of the training data, and so it makes the models sort of not safe for kids in an educational setting. Um, but you can also tell the models, oh yeah, where's that knowledge? Let's forget about that, and they'll reduce the amount of nudity that they produce dramatically. And so, okay, so this is just an example of like if you understand where the knowledge is in these models, it gives you these new tools to efficiently and surgically, take control them. And it's really, the control is really about taking responsibility, right? It's really about saying, oh, I think that before this, people would just be like, ha, it took us 6 months and $100 million of electricity to train this thing. And then they say, well, it does all these bad things. And then they'll say like, well, what do you expect? Like as if they weren't responsible for all of this, right? Because it's just so impossible to deal with. So the point of a bunch of this work is to show, no, it's possible to take responsibility for the work that you're doing. It's possible to understand the structure of what these models are learning and change it. Um, so that's sort of the technical aspect of it. The third aspect
David,
is, yes.
there's one question for you in
Oh,
the chat
yes.
about the last section.
Let's see. Question. Oh, in the chat. Oh, so many questions. I don't have the chat up. That's so interesting. Okay, what's the question?
Bettina, do you want to ask?
The idea is, would you have to look at all these? Yes. So this is actually Bettina. Yeah, you can ask Bettina.
Well,
Yeah,
I mean, I think it's very cool how precise you can be. And my question is
Yes.
just like, what's the sample size that
right,
would actually get you the output?
right. So the current, so I shouldn't oversell it. So the current state is that you can edit several hundred of these before you start to notice like the degradation of image quality. And so, maybe 500 or so. And so one of the issues here is that so that means in the current state of affairs, you know, you can take responsibility for 500 things. And then after that, we need more science to figure out how to do better. And so this would be I would say this is applicable today. If you have a few hundred things that are really high priority that you really need to deal with. But for the million other things that you might want to do, this is not yet ready for that. That makes sense? Yep.
And is there a way to identify what dimensions seem like there's a skew? Like,
Oh, I don't know what I want to edit. What's the worst situation? Um, that no, well, uh, let me think if I can say any research. So I'm not an expert in that question. That's an excellent research question. And I don't want to misrepresent by saying it's not known because it might be known by somebody. There's like so much research going on. But I don't know a good method for sussing out like what the worst bias amplification is in a model. So this is the phenomenon here is bias amplification, where you have biases in the behavior of a model that actually don't directly reflect the biases in the training data. So we know that there are biases in training data, right? That's unavoidable. But the bias amplification effect is when people carefully go and they measure the training data and the biases in the training data. What they find is that, in these diffusion models and a bunch of other sorts of situations like this, the output of the model is actually more biased towards like the majority concept than the training data was. Like if the training data had a certain amount of diversity, the uh, the the behavior of the model will have less diversity than the training data. So this is it's been observed in a bunch of situations, and there's a bunch of different theories for why this happens. But you can't blame it all on the training data, right? It's also has to do with the limitations of the model. Things go on wrong in machine learning. So when people say, oh, we're just reflecting the way the world is. Well, actually, a lot of these things don't reflect the way the world is. They actually amplify the biases. And so we definitely need to understand these things. So, okay. So a little bit of a couple side notes there. I think one of the things that is in our way here, and that I think relevant to this audience, is that what I've shown you is all these scientific techniques, and a little bit of a flavor of what kinds of things we'd like to be able to develop by looking at these things. But what I think is really important is to democratize this responsibility, right? Like I feel like you don't want a situation um, where so what got me into this whole field was this ratio. The ratio between how many people understand a system, like a computer system or technical system being used in the world, versus how many people are using it. And if you take the number of users and you divide by the number of people who understand the system, who can take responsibility for it, one of the concerns is that this number has been growing and growing over time. It's this huge overhang of like a larger and larger fraction of the people who use the system are ignorant of how it works. And and I think it leads to loss of trust, and it leads to a loss of responsibility taking, and even the ability to pin responsibility on the right person. Because if people have no idea how the system works, they don't even know how to attribute responsibility. And so the real concern that I have about deep learning at these large scales is that this ratio has gone to infinity, right? If you had a really large system, like I worked at Google for many years, right? The ratio is, in the millions, for every, 100 million people who use Google, maybe there's a person, a handful of people, there's only a few hundred people who really understand how Google works. But for these deep learning systems, the concern is the number of people who understand how they work is zero. It's zero. So people, it's popular to talk about the singularity. From my point of view, we're already there. This is a singularity. We're dividing by zero. There's a societal problem here. And so okay. And so where does this come from? So I think that there's a mitigation to this. And it has to do with the structure of the way these models are created right now. So modern large-scale AI is made up of two parts. There's this foundation model training, which is hugely expensive. This is the thing that you have to, put in the oven for a couple years and train it on vast amounts of data, and takes hundreds of millions of dollars. But then after you get this, then you have this fine-tuning process where you take this model that has all these capabilities that you've trained into it, and then you decide on what its personality should be, right? It's in this last stage when you do things like, oh, we're training this model in China, and I've got a list of 100 things that I'd rather this model not talk about. And so you fine tune the model to teach it that this is what it ought to be doing, the ethics that it should be following. This last bit of thing is the control that we put on top of models. And is that also the moment that you would use some of these interpretation methods that I've been showing you? Like, oh, we should fix what doctors look like. That only takes like 5 minutes to do. It doesn't take $100 million of electricity. And so the problem that we have is that we have mixed up these two things in our industry, where in order to do the second thing, at least in the US, for most commercial AI, you need to be in the company that does the first thing. And like if I had my way, and I just like set the law for the world, right? I would say these are two different industries, right? Creating the commodity foundation model, the pre-trained thing, the thing that costs hundreds of millions of dollars, right? That's like a utility, right? And then there's this other industry which is competing on making the personality of these AIs as useful and as good as possible. And the challenge that I see that we face is that because we're allowing people to protect number two with the moat of the investment of number one, we're going to get very, very little competition on different types of personality, different types of um, fundamental ethics in these models, and that I think that worries me a lot. And so, and then I also because of this structure, because of the mysticism around phase one, I think we're not being set up to take enough responsibility for step two, which I think people can take responsibility for. And so, so anyway, so yeah, so this is the point I made. This is like $100 million. This thing down here is like $1,000. And why is it that, like all the societal impact is in the $1,000 thing? Why are we letting people protect it with their $100 million moats? Now, there's some models that are released open, which I think is great. Um, and and so there are, but there's still like practical problems for this because if your unit of training is like a $1 million computer, which it is for some of these big models, then even if you release all the model weights out for the public to see, in order to run the model, it still costs the same $1 million, right? Unfortunately, right? Like so, the capital cost of actually using these large scale models, even when they are open, is quite high. There's no discount. You have to have similar hardware that we use to train it. And so this is why we're failing to study large scale AI for both these reasons. One is because we have a proprietary culture around the very largest ones where it's just not available for people to tinker with. And then even for the ones that are open, which is the brown line here, there's high capital cost for getting into it. And so there are very few labs that can work near this line. Basically, nobody's working on this line except for people who are using NDIF, right? And so, so the average, capabilities of the models that academics are studying is this blue line down here, right? Really, really far behind. And so, we need an ecosystem to build the science, number one, to build the science, number two, but really, especially to build the culture, number three, that this is something that we do, that this is not something that, you hope maybe that somebody at one of the big AI companies does, but this is just, we need to figure out how to make this our responsibility as, customizers of AI, as deployers of AI, as consumers of AI, that this is what we do. We take responsibility for it. We understand what it does. We take control of what it does, right? And so NDIF is an infrastructure for doing this. So what NDIF is uh, there's a bunch of technical charts I have here, but basically what this explains is that NDIF is an API. So just like, when OpenAI decided that they were not going to release their model weights when GPT-3 came out, they said, oh, the thing that we have to do is we have to create an API so that people can just send us their questions and our AI will give them the answers. And so they created an API for using AI remotely, which has become kind of the standard for how all the companies um, deploy their AIs. They all have like OpenAI compatible APIs that are they're all black box APIs. You basically you give it input, you get output, and you get no insight about what happened in between. And so what NDIF is a reimagining of what an API would be in a white box world instead of a black box world. And so the idea is instead of just giving inputs and getting outputs, you give it inputs and then you give it modifications for how you want to affect how the neural network runs. And then you get these modifications back. So these modifications, there's this little techie thing here. Is these little graphs that we send over. They come back and we get back the result of not just running the model, but running the model with all these graphs, all these extra instructions interleaved into the network. And this is actually really flexible. This lets you ask, what is the model thinking inside? What is it representing? If it was thinking this, can I change it to do something else? And so, okay, so we have a team doing it. And so here's just a little bit of example code for the API. So here, if you're a PyTorch programmer, then you'll recognize that when you create a PyTorch module, a neural network, you get an object back. So this thing is actually a PyTorch module, um, which represents the Llama 2, one of the Llama 2 language models. Normally, when you have a PyTorch module, you use it as a function. You would call it by saying lm parentheses some input, and then it would give you some output back. And you can do that with this. This is just another PyTorch module. But because we've imported it using Nsight, these modules all have this extra way of running them called trace, where if you run the model under a trace, then instead of it just being a regular function, it becomes this with statement, where inside the with statement, we can write a bunch of code, which is the code that says, here's how I want to change what this model is doing. And you can write arbitrary code in here. So we're going in, we're saying, hey, at layer 14 of the model, grab this input, stick it here. Take this thing and then turn these 3 neurons on, flip them up to 10, and then grab some other vector out of the model, read that out. And then after I'm done running the whole thing, I can print this out. And what this does is these are the 3 neurons that cause the model to do the opposite of whatever you asked it to do, right? So this is really interesting. So it turns out, if you understand the inside of the model enough, you can find opposite neurons. And so if you flip these 3 neurons on, instead of it saying the truth is the truth, or to be fast is to be quick, or to whatever, right? You can flip on these neurons and it'll say the truth is the lie, right? To be fast is to be slow. It'll say all sorts of stuff like that. It'll say the opposite of whatever it is that you were asking for. And so this is just an example of like how you can do that in just a few lines of code. Obviously, you can write more code in them. But you can also see how this is way beyond anything that OpenAI or Anthropic, whatever, would let you do through their API. You can't reach in to these models and ask, what do these neurons have in them? What would happen if I flip these neurons around, or any of the other, hundreds of things that you might want to do inside a model. And so that's what NDIF is. And so basically this was a dream that we had a couple years ago. We submitted it as a project proposal to the NSF, and we got an award to build this system. And so we created this API on the left, all the little blue chunks. We have this wonderful engineer who designed this API, Jaden Fyodor-Kaufman. And then after we got the funding rolling, we created machines in a data center and a cluster to run the backend. On the right, the thing that I didn't explain to you is that you can do this. You can run this locally on your own GPUs, but if the model is really big, you can just go to the trace and you can say, hey, I want to trace this function, but I want to trace it remotely. So you just say remote equals true. And then your code and your request gets packaged up and sent over to these green boxes on the right, where it's run like an API request, and you can get the results back. And so it's designed right now not for commercial deployment, but for supporting scientists. So in the US, we have these various scientists who are using it to develop their research. And there's a whole bunch of preprints that use NDIF technology already in the first year. The refusal directions research, some psychology research. There's like some biology research. There's like research on a bunch of different things. So we have a couple URLs that you can look at if you're interested in NDIF specifics. But this is more or less. So I spent most of the time trying to justify why it is that we're doing this, and just a couple minutes at the end on we're rolling. So but the status of the project is we're about a year into it. We've more or less figured out how to build the software that is running the system. We're actually running it on live users, and so we had a few hard lessons in our first year of things that were difficult to get right. I'm hoping that we learned the hardest lessons so far in the second year. We can take advantage of that and continue to make the system work really well. But yes, but it's running right now. So okay, so I think that's my talk. Sorry to be a little bit rushed at the end. I sort of went a little bit slow, but yeah, there's information about the project. Thank you all.
It only got more interesting as you got to the end.
Okay, sorry about that.
No, this is
Yeah.
fantastic. Thank you.
Great.
Let's see. Are there any immediate questions on the first 9/10 of the talk? And then maybe if you have time, it would be great to hear a little bit more about what you think you did learn from year one, and
Oh yeah, sure.
and the interest that you've gotten from places outside the US, because this is constrained to users in the US.
That's right. And I'm very excited that Sigurd and Carsten are here. I think that when we started the NDIF, in different administration, we had some early conversations about, can it be a global project and so on. And there's around AI, especially, there's been a lot of sensitivity about geopolitical competition. And so even when we were applying, the recommendation was, start off by focusing on the US because there's special earmarked funds for US only work. And then after we get going, we can have these other conversations. I think that now it's maybe under the current political climate, it might be difficult to have those conversations formally through the NSF. But I'm very excited to see Sigurd and Carsten independently pick up their effort to take some of these technology ideas and find European funding, independent European funding for it. And which my understanding is that they are in an early pilot phase of that, but that they've started the ball rolling. Is that right, Sigurd?
Yeah, that's totally right. That's totally right. We are in the early phase. We have done the first feasibility study in our area. We were totally thrilled by your presentation in the Vienna ICML conference in 2024, I think it was, on the mechanistic interpretability workshop. And we had a situation before that we have done a little bit of stuff of the mechanistic interpretability, but had this issue what David described in the whole presentation, that we are a small institution. We had a little bit of money to buy servers and stuff like that to do our work. And our researchers in our team has then used PyTorch and hooks and stuff like that to find out how we understand these models. But then the hardware was intersecting between the users. So one user has blocked the whole machine, and then the other could not work on that and things like that. And we saw the presentation and said, oh, that's very great. That's a system where really research in mechanistic interpretability can be democratized in teams, but also over institutions. And therefore, we thought it would be good to try to set them up in Europe and try to find out if it's interesting for Europe. So that was the first question. And the second, are we able to, perhaps I don't know where you're from, but in Germany or Europe, we have from Germany directly. But in Europe, you often have different countries and there's situation between the countries. So it's a little bit more diverse, I would say, somehow. So we were not sure if it's possible that researchers from Europe has interest that it's somehow not really centralized, but starting from one organization out to a project in Europe. And we find out in the feasibility study that it's totally open and that there's a high demand on community in Europe to really do the research, but also have the possibility to get access to bigger models and therefore democratize the research even to really small institutions or even individual researchers. And we are right now at this stage. We have a little cluster running so that persons from Europe can also use that, but not on a high demand. So it's not really that we have huge compute power right now, and we are in the funding phase for getting more funding for more research or for more compute power. And then also for doing research on this stuff. Yeah, that's a very short.
Very exciting. You know,
Mhm.
I think Sigurd's team has rewritten a whole bunch of, of course, as typical for a research project, our code is all open source. And and naturally, it all just runs without modification, right? No, actually, Sigurd's team has had to develop a bunch of modifications to get it to run their environment. I'm very impressed with the things that they've done, and it's it's very exciting.
Thank-
And so so I think uh yeah, so now you have no excuse. If you do research in this area, and you're in the US, you should use our system. If you're in Europe, should contact Sigurd, get on his pilot. If you're somewhere else in the world, then you take a look at what Sigurd did. Yeah, you can set up your own. You can call up the authorities, get some funding. Um, and so yeah, anyway, okay, so Josh has a question.
Hey, David. As always, inspiring work. The So my question comes from the right now, at least these days. I'm doing a lot of work and trying to understand the kind of industrial sources of inference. So, like, billions of dollars getting spent on inference infrastructure to power, obviously not typically scientific workloads, but just like
Right.
typical consumer workloads or
Sure.
enterprise workloads.
Right.
One of the questions I have is like, how could I use this interpretability research and this sort of the stuff, the progress you guys have made on building this, this new form of white box API? Is there like a way of maybe like constructing what I think of as like a power user API when you use, NDIF and your existing interpretability kind of workflows? What extra power does that give you versus, like doing some sort of just in context learning, editing the context, adding some instruction?
Right.
So I'm just trying to figure out how could I use this as a kind of build this out as a feature effectively
Yeah.
for bigger inference scales.
So I think we're pretty much in the scientific phase right now, which I think is um, let me make an analogy. So when biology sort of cracked DNA, one of the early pieces of infrastructure that showed up was like sequencing machines, where you could sequence your DNA, and then maybe other things for like assembling arbitrary pieces of DNA and things like that. Like there's different pieces of technology there. So could you take a sequencing machine and like use it in a hospital as part of treatment? You could. It might not be the right thing, right? But it does like turbocharge science. And once you like turbocharge science, it allows the scientists to take responsibility and understand like what's going on in a lot more detail in these mysterious biological systems. And once they understand that, then you can turn around and deploy the things. And so for example, um so I think that realistically, this is where NDIF is right now. Now I think that um, now computer infrastructure is always a little bit more fungible. So I think that there is a world where, um, we, if people decide that like steering vectors or some of the other interventions that you can do inside neurons, that you can change a model's personality by just tilting its activations in certain ways. And if people decide that this is the kind of monitoring and control that they want, NDIF could be used at industrial scale. But the current implementation of NDIF is optimized for transparency, so it runs some factor slower than inference systems that are optimized for speed without transparency. I don't know if the factor is 2 times slower or 3 times slower, but there's some factor of slower that we run. And uh, so there may be industrial users for whom that doesn't matter, and they want more monitoring and more control. Um, but right now we're sort of focused on the scientific, uh, part of the usage.
Maybe another way of just posing the question really quickly. Just
Yeah.
Is there a user that is not your like typical interpretability researcher right now of NDIF? Who is there an
Yes.
outlier in your user base that's like using it for things that you were kind of not expecting?
There are some. There are some. So I'd say that there are maybe 3 patterns of use. So we have a bunch of outliers. We've got like there's um uh I some of them I'm still trying to understand. Like so for example, we have political scientists who really want to understand what the LLMs are thinking inside. For them, this is an amazing opportunity. Like they've been dreaming for years about cracking this puzzle of like when they interview a person, is the person telling them what their real political beliefs are, or are they just lying or whatever? They wish they could like put the person under a CAT scan and see what's going on, or give them an MRI. And so now that they have LMs, they sort of my impression is they're presented with this opportunity to look inside the LMs to try to answer questions that were unanswerable about humans. And but I don't understand in detail like what they're doing, but some of the political scientists are actually quite technical, and they like before they knew about NDIF, they were busy trying to build their own software systems to do some of these things. And as they've come in contact with NDIF, they've started to make things, use a more common language with the rest of machine learning. And so we're learning from folks like this. Some people are using NDIF not to look inside the neural networks, but just because they're scientists who need a well-supported scientific environment. They need to run bigger models that they don't have the capacity to run, and they could go to a commercial offering, but they um, worry that if they use OpenAI or something, then they don't know what they're running because tomorrow it's different from today, it's different from yesterday, and without any announcement. And so there, we do have users who are using us maybe mainly for reproducibility or other types of transparency. Um, that makes sense. Yeah, but just a few of those. All right. I can if people have rude questions they want to ask me, not on the recording, I'm happy to stick around also and chat. Sam, you want to be recorded?
One last question on the record,
Okay.
which is if people want to, let's say someone who had the option of using commercial providers wants to use NDIF, is there a mechanism for them to pay NDIF what they would have paid another provider?
Oh, not yet. I'd love to figure out a partnership. So one of the things that we're doing is we've taken one of the NDIF staff and put them in Silicon Valley, and so partly to start conversations with Amazon and whoever else, right? Like the major hosting providers, to see if there's any interest in them having a commercial offering of NDIF that people can just pay for. So right now, if you want to use NDIF, it's under National Science Foundation funding, which is limited, and you sort of have to be an NSF researcher to use it. Um, and now that's actually pretty permissive. And so if you want to try NDIF, I encourage people to just, come along and use it. But if you feel like, oh, I've got some commercial use of it or something like that, or I should pay my own way, I'd like people to be able to use use Amazon or something like that, and get as much capacity as they want. And but that's not, we don't have any commercial providers, commercial partners right now. But it would, we think it would not be hard for them to offer something.
Fantastic. Well, with that, let's close the recorded part of the session. Really greatly appreciate it. And I see.
Perhaps per tradition, we could all briefly unmute before we turn off the recording, and give David a raucous round of applause for an amazing presentation. So let's count down. 3, 2, 1. Thank you so much, David. This has been great.
That's so nice of you. Thank you. Very nice. My pleasure.
Wonderful. I think actually you need to turn off the recording if you've been made the host.